Hi, my name is Aleksander Iskhakov, and I'm the CTO at Tools for Workers. And today I'm talking about optimizing container synchronization for frequent writes. I know the name of the speech is pretty mouthful, so let's dive straight into the topic to see what lies behind this title. And actually, it's a very important aspect of a multi-threaded environment, synchronization. Here comes the time when the bottlenecks cannot be resolved with just architecture or buying some new hardware, but should be done with optimization of actual handling of the data in code. So we will look at some common practices in container synchronization and how they struggle to address the not really uncommon situation of frequent write operation for multiple threads and what can actually be done about it. I will illustrate my speech with a bit of C++, but I will keep the conversation high level enough because principles that we today are discussing can be applied in any language of your choice. And we'll start with the example by changing some abstract container for something real that maybe hits home for some of you. It's some transactional cache. Let's have a map, a dictionary with the key being user ID, and a value is dynamic array of transactions. You can see that transactions are actually structs transactional data, and it's actually just some data about the transaction, such as date, amount, type, whatsoever. It's not really important to the conversation. What's important is that maps in C++ are binary search trees. And the important thing to know about that is that we can access or remove an array of transactions of each user by ID in logarithmic time, which is pretty great because that makes this particular cache applicable in many situations. And let's say that we have 3 cache operations. So read, when we just reading this array by some user ID, write, where we put transaction in the cache, and pop, where we just retract accumulated transaction from the cache for example, following processing. And if the cache is accessed by different threads, for example, by tasks in some thread pool, you'll need synchronization. Otherwise, alongside with obvious data races, you will keep getting all sorts of errors in situations like, for example, when the tree balances itself after pop operation and simultaneously you try to write new transaction by, no longer valid address. So you need synchronization. The simplest approach is to lock the container with Mutex. The lock can be acquired by one operation at a time, and other operations will have to wait to acquire the lock for themselves. This is pretty easily done. In C++, you just use lockguard locking the dedicated, and this will work in terms of synchronization. It will synchronize your data and avoid the situation I described earlier. But if load increases, the operations will have to spend more and more time waiting on locked mutex, and more and more threads in your pool will do nothing but wait for the lock. So sequentially, transactions in your systems are being processed with significant delay. That's not right, and we have to do something. What can we do to improve this situation? One of the approaches, I would say it's a next level approach, is to use reduce writer lock. In C++, it's done by using shared mutex and shared lock. And let's actually head back for a moment. Let's say that here a load is caused by constant need to check transactions. So most of the time most of operation in this load actually read operations that not change the cache. And reduce writer lock works perfectly here because it allows 2 types of locking. First one is unique locking that we use for write operations. It's actually done with the same lockguard as with the simple mutex, and mutex locked by this unique lock actually behaves just the same. So both readers and writers wait for the lock. But what we have different in shared mutex is that it also allows shared locking. And in this scenario, when the shared lock is acquired, all the shared locks can be acquired simultaneously. That's why reading can acquire simultaneously, and we spend less time to wait for lock to be freed. In C++, we can use shared locking by just, using std shared lock with shared mutex. And this actually works like a charm in read-heavy environments. Basically, while you have a read operation, they are done simultaneously without any locking, just as is there no mutex whatsoever. To put it simply. Of course, we occasionally have to lock uniquely, and all operations have to wait for the write operation to pass. But if write operations are not too frequent, that's not a. But let's imagine another scenario. What if we have read-heavy environment? Obviously, the benefit of the reader's writer lock doesn't work here, and we have to be more creative. But first of all, let's define this write-heavy environment, and we can just do that by simply removing read operation whatsoever, just by having write and pop operation. For example, we have cache where we need to store a lot of transactions that are being bombarded from all different threads, and then occasionally we have to acquire collected operation and remove them from the cache for further purposes, for the processing with the operation. And both read and pop functions changing the cache. That's why we are dealing with write-heavy environment. As we mentioned earlier, reader's writer lock is pointless here, and we are back with a simple mutex with one operation at a time, and we have to somehow improve from here. And to improve from here, let's look at the data structure and how we work with data. You can, actually notice that each operation works with only one user. And the approach that asking to be implemented, it's if we could process each user separately. That naive approach is to divide our cache to a lot of caches with just one user and the separate mutex for each one. But then, of course, we have to put all these caches into one container, and this container of caches would have to be synchronized too. And that's when we are back with where we just began thinking about it. So I have a better solution, but it roughly follows the same principle. Actually, you maybe heard of the word sharding before, and you probably heard this term in the realm of databases, but it's perfectly applicable in our scenario. So like in the previous naive approach, we're still splitting our original cache, but we are splitting it to a preselected number of shards. And then we just have to decide how the data would be distributed by those shards. And let's say that in our example, distribution of transaction among users is pretty homogeneous. And we want to split cache to 4 shards. Of course, we can split the range of our user to 4 parts, just start, then the second quarter, third quarter, and the last quarter. But if we are talking about this somehow realistic scenario, the users with lesser ID are probably registered earlier and maybe less active than the users with ID closer to the top. So to combat this, let's just use modulo 4 as a distribution function. So here we have it, 4 shards, and when we have user ID, we just decide in which shard it goes just by applying modulo operation. Of course, all of those 4 caches should be wrapped into interface to appear just as one cache, but it's pretty easy to do. We have a vector of array of 4 pointers, and we figure out necessary index in the vector by modulo operation. That's what's important to note is that we don't need additional synchronization for the vector itself. because no matter how writes and pops we do, those 4 maps are always there by the same address. And yeah, if we synchronize each of them with their own mutex, we are fine here. And look, now we have 4 simultaneous operations. What if we think that 4 is not enough? Can we have 10 or 100 shards? Would it practically help? That's where I have to run the tests and check it. Here you can see the comparison between using just simple mutex and sharding with the different amounts of shards. A load here is around 2000 write operations, 300 operations per second, and the concurrency is 8. The concurrency is the amount of threads that can be run simultaneously in the environment that I'm testing on. So here you can clearly see relatively how much time each operation wastes on waiting for the lock in the first scenario. Of course, in all of the scenarios, the average time to process the operation is less than a millisecond. But this is just demonstrative tests. In real systems, the data is often much complex and the processing of them is much more sophisticated. It may require additional computations, access to other data, other caches, and this can significantly increase the time on the operation itself. So it's good to spend as little time on synchronization as possible. And in this regard, we can see that sharding approach will basically eliminates all the waiting for the lock. But in regarding to different shard sizes, we see that my tests don't show significant difference. I suspect that the minimal effective value is tied to system concurrency. And my concurrency on the test is 8, but of course on modern server machines it can be much higher, and shard sizes in these scenarios will be even better if we increase shard size from 4 to some numbers closer to the concurrency of this machine. Of course, that's just my hypothesis, and I will share the code for the tests at the end of the presentation. And I would like to hear maybe your feedback whether this claim gets proven or disproven. You can also note that the largest size tested, 100,000, effectively matches the mentioned earlier approach of assigning a mutex to each user, because in the tests, user ID generated within a range of 100,000. I've not seen any advantage in the processing speed, although this approach obviously more demanded in terms of memory. So we can write this naive approach off and just simply use sharding. Also, I've run other tests with a lower load, just 500 writes and less than 100 pop operation per second. And you can see that effectiveness of sharding optimization decreases. It's important to remember that the difference between a simple mutex and the sharding approach exists only because of a large number of transactions of the same times, causing a queue to build up. When we don't have this queue of operation waiting for the lock to be freed and then to acquire it and actually do the operation, simple mutex do the job. And this is yet another reminder that premature optimization can complicate the code without significantly impacting the results. To wrap everything up, here's the main points of the presentations. First of all, if you have data with predictable distribution and allowed parallelism by specific key, you can use sharding to significantly optimize processing time and avoid bottlenecks. Second thought, this is just one example how analyzing the data that you have can help you with optimization. So be creative and maybe try other ways how to approach synchronization. And at last, beware of premature optimization. I know that maybe it sounds contradictory to the previous point, but actually they work even better together. It's crucial to understand the application requirements and expected load. And that would be it for today. Here's a link to the GitHub where you can find the implementation of all of the caches that mentioned in the presentation and a code for the tests, so you can run it yourself. And if you have any questions, or maybe you stumbled across something interesting in your tests, you can write me, and well, I would be glad to hear from you. Thank you for your attention. Thanks to Conf42 for the opportunity, and have a great day.